Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about recuperator. So let's dive deep into it. So let's understand what is the idea here. The idea is that energy is in high demand. However, energy is unlike everything else. For example, many times we have high demand, which leads to high production, which leads to price coming down. Energy is completely opposite of that. The more we demand, the more we make, but somehow the price still keeps going up. So it's becoming expensive. Now, wasting energy is harmful to the planet. But let's say you do not care about planet, you do give a damn about your wallet. So wasting energy is bad for your wallet. So either you care about planet or you care about wallet, but you do care about it. So wasting energy is not a wise decision here. Now we do have waste heat everywhere. Every single direction you look at, be it industry, be it corporate, be it households, everywhere you look we have wasted energy. So that creates a very serious scenario where we have way too much waste heat. Now, if we can recover this waste heat, it can improve few things. Of course, it's not going to change the world because again, waste heats are generally at lower quality of heat. It's not like top quality 400 degrees Celsius heat. It could be very low quality heat. So in those low quality heat, you can still do some things. For example, you can improve your quality of life. I'll explain that further. You can improve fuel economy, directly helps your pocket, improves your electric bill consumption. So it's one of those things that it's wise to do, financially speaking. So what's the logic behind it? Logic is, let's go to the physics level, basic level. Basic level is that there is no such thing as cold. Do not fall for that. There is no such thing as cold. Cold simply means absence of energy. Energy goes from place where it has a lot of energy, goes to a place which does not have energy. So for example, let's say this is the sun, this is earth. How the heck this convection is happening? Not convection, basically transfer of energy is happening. It's happening through photons. Photon is bombarding the earth and earth atmosphere, and basically everything on earth is getting bombarded by that photon blast. That photon is like starting to agitate the molecules. That agitation is the hot part that we feel about or complain about in summers, especially in India. So heat always flows from hot to cold. Does not matter how, it will flow. Like it can jump through vacuum. If you are connected by some material, it will go through conduction. If you have atmosphere around it or gases around it, it will use convection. It will move. This puppy moves. Do not discuss about that. Like this puppy just moves. Now it works for both heating and cooling. For example, if you have a hot tea or hot coffee, and let's say that puppy is 75 degrees Celsius, you put it in a room. And even in India, let's say the ambient temperature is 35 degrees Celsius, the coffee still gets cooled to 35 degrees Celsius. How the heck that happened? Atmosphere is sapping the heat away. Basically the heat is jumping from high potential hot part to cool part, which is atmosphere, from its vantage point. So energy goes. So your coffee gets cold, and it works in other also. For example, you put an ice cube there. That ice cube is like very low energy potential. Room is boiling from its point of view. So a room is like same thing. So it melts. So it works in both direction. Now the core aspect of every engine you have to understand is that how much work you can get out of it is directly proportional to degree C delta. Meaning, if your ambient is 50 degrees Celsius, let's say India, and your basically combustion is giving you 500 degrees C, that means you have temperature delta of 450 C. You can get some significant amount of work done. But if temperature delta is, let's say, very low, for example, let's say you have 50 degrees C and you got your heat that is 70 degrees C, you only have 30 degree temperature delta. So you're not going to get much done. So that's why whenever we use fuel, it does not matter which kind of fuel, does not matter where we use it, be it nuclear, be it coal, be it natural gas, be it biogas, be it whatever the hell, all you are focusing on is making it hot. Basically, air comes in and it becomes GG amounts of hot as you can make it. As long as your metal can survive it, like of course there is a limit, because you can make it super duper hot, but if your metals melts, no point in that. So this is the core limiting factor of how much useful work can be extracted from any fuel, be it jet fuel, diesel, petrol, whatever have you. Now, what's the key here? Well, like, how do you control the vector of energy transfer? That is surface area or cross section. Basically, this is one of those puppy that are used to cool coal power plants. Coal power plants produce GG amounts of pressure and temperature. Now pressure goes through the turbine just yeeps, basically yeets the pressure out of there. So it can go in like as high as like few thousand psi. Not few thousand is a bit extreme, but you get the point, like very high pressure, and the outside would be partial vacuum. So it removes all the pressure, converts it into electricity, we get electricity, awesome. Problem is still hot. The temperature does not drop that much. So what we do, we basically cool that puppy. So cooling that, we have to utilize this puppy, because even if you have, let's say, a loop, a water cooling loop that is connected to a river, which can truly cool it down, problem is, how the heck are you going to dump the energy? Because energy dumping rate is directly limited to the cross section. How much area is there for things to intermingle, basically vibrating molecules to attack non-vibrating molecules? That's all there is to it. Basically vibrating molecules, non-vibrating molecules. You want vibrating molecules to go to non-vibrating and starts to vibrate. That's all there is to it. So we do something like this, which we call tube and shell heat exchanger. So you have boatload of tube, steam goes into the tube, and because the tube is surrounded in a casing, and casing has like a lot of high pressure water going through it, or maybe sprayer depending on the design, and it just yaps the heat away. So that's the logic behind it. So the larger the surface area, the more the oomph you can transfer from A to B. This directly controls your efficiency, meaning let's say you do not have too much temperature delta. Let's say the hot is not really that hot, cold is not really that cold. In that sort of scenario, you really need a lot of surface area. If you try like, what if I have like, small 1 square meter of surface area? It's like, nah bro, you have to start with like a 100 square meter area. Then you go to 5,000 square meter area. So that's the logic behind these things. So we use the first technology that we call air handling. You have to understand this. This is modern understanding, simply because back in our old days, our buildings, while we added air conditioning very early on, we did not build a seal building because energy was not such a big concern. People were just like brute forcing it. Now, as it became more important, as planet got bit hotter, we started to realize it's like, hey, our bills are coming higher. So what if we seal the building? Then it created a paradox. The paradox is that we create a lot of heat. For example, let's say you are working in an office. You can calculate how much electrical energy is going. Let's say for computers, you're like, okay, whole computer is like, let's say electrical panel load is 10 kilowatt. You're like, okay, 10 kilowatt, let's put 12 kilowatt as buffer. Okay, that's your electrical load. How many people are there? Of course, most time people will calculate it. It's like, if everybody is lazy, that's 100 watt. If everybody is active, they are doing something, and they have high blood pressure, you are looking at 250 watts of heat output. So you will take high blood pressure, multiply with every people, and then you will calculate how much heat load just the body heat is creating. Then your air conditioner will be sized accordingly. Everything is awesome so far. And then we forgot that people also emit CO2. Yeah, and our body is not trained to detect low carbon, basically low oxygen. It's designed to detect super high carbon concentration, meaning if CO2 percentage goes a little higher, we starts to become drowsy. If it goes as high as 13%, you directly go up. Directly. That's a direct ticket. Like very serious. Like we are surprisingly vulnerable to CO2 poisoning. Surprisingly vulnerable. So we really created a scenario where our modern office building, which is completely air sealed, very good energy efficiency, was literally coming at a side effect of like CO2 poisoning. Now our body does recover from CO2 poisoning very well. So that's the good part. It's just that it's not really a wise thing to do 8 hours every day. So we realized very early on that air circulation has to be there, otherwise we will not be functional. As you put more and more people, even if it's cool, even if it's flat out cool, people will not know why the heck they are so sleepy. Many times people will say, I'm sleepy because it's cool. No, you're sleepy because you may have serious CO2 poisoning. Your body is like, I'm like, basically body is underclocking itself, so to say, to protect itself. So you want to bring outside air. Again, outside air will barely have even like 0.1% of CO2 concentration, barely. So you want that air to replace with air that, like, stale air that could have as high as 3%. So you may be like, okay, what can we do? Here's the problem. Outside air is outside air. What do you talk about when you are talking about air conditioned unit? Air that is conditioned, meaning its humidity would be controlled, its temperature would be monitored. So if you directly try to dump that kind of hot air, for example, in India, the indoor temperatures could be generally around 20 degrees Celsius. Outside could be generally 50 degrees Celsius. If you dump 50 degrees Celsius directly inside, the air conditioning unit would be like, first I have to take care of the electrical load, then I have to take care of human body heat, then you put this, yeah, I'm out. No air condition can do that long term. Like, of course, burst load for a little bit, not for long term. So how do you take care of it? It creates such a ginormous amount of thermal load on the air conditioning unit. Air conditioner is like, bro, I'm out. I'm flat out. So what we do is heat exchange. Heat exchange is the key. Thermal exchange, basically, or you are not mixing air. It can be done. Some designs do mix it, but generally it's not preferred. Like you do not like the idea. Like most people times, it's like do not mix airs if you can avoid it. It's just like let the bad air out. Just let it go. Let the high CO2 air go, and bring in fresh air. So what you will have is an ecosystem like this. Now, how each company does that, how each vendor does that, that's up to them. But the logic always remains the same. Basically, you have hot coming out. Basically, that is 50 degrees Celsius. You have air conditioned air that you want to exhaust, but it has a lot of CO2. That air goes through the counterflow. Now, what's happening here? You have a lot of temperature delta, 30 degrees Celsius of temperature delta. So what happens is the air that is coming from outside cools. Why? Because it detects there is a basically cold side. What is the cold side? It's the exhaust air that from your building, that is 20 degrees C. It's like, okay, I'm gonna heat that puppy up. Now, in doing so, energy cannot be created nor destroyed. It loses energy. It basically gives off equilibrium amount of energy to the other flow, that is you are exhausting. Consequence of that, it becomes pre-cooled. Now your air condition is like, okay, I get it. Rather than directly trying to cool 50 degrees Celsius air, it's trying to cool something that is more close to 30 degrees Celsius. That temperature delta of 10 degrees C is like air condition is like, it's heavy, but I got this. And you have no CO2 poisoning. That's awesome. And during COVID era, everybody was like running this puppy on max load, because it turns out it's actually desirable. If you have any sort of contagion, it's generally a good idea to keep circulating the air. So that's awesome. And it also works in winter, especially necessary for people in the basically northern areas. So because here's the deal, India knows hot, Alaskan knows cold. So their cold could be like, let's say, minus 50 degrees C. So at that point in time, if you directly drive minus 50 degrees C into your building, your heating system would be like, bro, I'm out. So what you do, the exhaust that could be heated to, let's say, 20 degrees Celsius, you send it there. Now 50 degrees Celsius will try to absorb as much heat as possible from 20 degrees C. 20 degrees C drops to, let's say, minus 10 degrees Celsius, but your minus 50 is heats up to, let's say, 0 degrees Celsius. So now your heating element is like, I got this. I can heat from 0 to 20. So it's the same thing. Either you pre-cool hot air or you preheat cold air. The one will be done in winter, one will be done in summer. And this is a completely passive device. The only consequence is that because again, you have heat exchanger, it does have restrictions. So your fans consume a little bit more power, but it's minor. It's like, especially if you have clean air filters, it's a very, very minor flow. But sometimes if you are really serious about this, you can just ditch this heat exchanger, passive heat exchanger, and just put two basically condenser and evaporator with a two-way valve compressor in between. That point you can just because here's the deal, the heat transfer can only happen as long as equilibrium is not reached, meaning this is your outside and inside temperature. It does not become like this. All it does is like this. Equilibrium is reached. So if you have like, let's say, cold, that is like, you have hotted air and outside is cold, it will not be like, it's not a flipping mechanism. All it does is brings it equilibrium. That's why it's specified. It preheats or pre-cools. It does not just does everything that you need to. It's just like makes it much more easier. Removes the wasted energy. Like the energy you spent on cooling is no longer wasted completely. It's still wasted, but not completely. But if you really want to maximize efficiency, you can just put a basically phase change cooler there to improve that system. It does add cost, does add one extra more compressor, but many times it is desirable, especially if you really want to maximize the efficiency. So that's something that can be done, and it does save energy. It does save from CO2 toxicity, and be mindful, equilibrium temperature. Do not think about like my hot is like exhaust is 20 degrees Celsius, outside is 50, so that 50 will become 20. No, it will reach equilibrium. So till equilibrium it will work. Unless you want to push it beyond that, then you have to run an air conditioned unit. And there are small units that are being under construction right now, that is for homes, simply because European homes have to deal with a lot of heating bills, and if they have like a lot of people running around, it creates a scenario of CO2 poisoning even inside a home. So they do need fresh air circulation, but if they directly let the cold air in, their heating system would be like, bro, I'm out. So this sort of small basically chimney kind of style system is being worked on to improve that situation. People have built it out of styrofoam in their home also, so it's like it can be done, but do not expect the efficiency of a professional one, but you will get something better. Then we come to, that's the recuperator for low temperature. What about the high temperature puppy, like jet engine? Now fuel in jet engine is only used to do one thing: heat the air. There is nothing more than that. Just take fuel, heat. Like basically air comes into 50, you want it 500 degrees Celsius. That's all there is to it. That 500 is the one that is doing the work. So What if instead of 50 coming in, what if you have 200 coming in? Now you need less fuel, because again, all you need is that 400 degree C air. The outside air is still 50 degrees Celsius. So that's all you need. So you can reduce your fuel consumption. That will directly improve your profit, which means your wallet will be happy. So that's how it works. Now here's the deal. The logic, the principle, all are known sciences, old technology even. Then why don't we use it in plane? It does add weight of a heat exchanger. Of course, you are adding a heat exchanger, so it does add weight, and planes are very weight sensitive, so people generally do not try to add weight to it, even if it improves mileage, because there is a contradiction here. It's like, yeah, it's more efficient, but you are hauling the more weight. It's like you might as well have not added the weight, reduce the basically reduce the complexity, and just cut better mileage simply because it's less hassle. So that's why it's not generally seen in aircrafts. However, but when you're talking about some big puppy like Abraham M1 tank, this puppy has no weight constraint. They're like, add as much as weight as you want. This puppy is 60 tons or maybe even 70. So they took basically apparently it's an old surplus of helicopter jet engines. That's how it started, and this is the jet engine. Now here's the problem with that. It's a jet engine, meaning the exhaust is hot AF. If they directly exhausted that, nobody ever had to aim for Abraham tank. They will just fire a heat-seeking missile in that general direction. The moment the heat-seeking system goes downwards, it's like, I can see it. They won't even need to worry about aiming anymore. So they were like, yeah, if we launch this in battlefield, yeah, bye. Poof, our tanks, heat-seeking missile, poof, nothing more than that. So they put us something amazing known as recuperator. So idea is you take air in, normal ambient air. Now you compress that puppy. It heats up a little bit, but it does go up in pressure. Now you take that, you send it to recuperator. Now after recuperator, you add fuel, you add ignition, voila, you have jet. You have very high temperature exhaust that is doing your powered coupling and all that jazz. You got that, and then the hot exhaust is very hot. It's like as much as like 600 degrees Celsius. At that point in time, that goes into the recuperator. Now recuperator is trying to marry two things, basically the high pressure but lower temperature compressed air that is circulating, that will be fed to basically combustion chamber, versus the exhaust that is trying to dump its heat. So your exhaust goes down from, let's say, 600 degrees Celsius to 300 degrees Celsius. Your intake air goes from 150 degrees Celsius to almost 250 degrees Celsius. At this point in time, your fuel load goes down, meaning how much fuel you need to drive this puppy goes down considerably. Be mindful, this took quite some attempts to get it wise enough, because the first Mark 1s they tried, it's like, nah. Mark 2, Mark 3, by Mark 4 apparently it's like, yeah, finally they figured it out. Of course, it's a complex technology. We do not use it in helicopter simply because the recuperator is very heavy. So this does work. It's a known technology. It has been used in other things also, but M1 Abraham is very popular and known system. So that's here, and people are trying to put this in air also. Specifically, there is a niche case where you have microjet engines that are used for Cessna and all that. Now it's not used for Cessna simply because microjet engines cost same as a basically full side jet engine, but gives you much worse mileage, because again, jet engines do need speed. The same reason why M1 Abraham is used, because like everybody's like, oh, it has bad mileage. It does not matter. If this puppy starts to chase you, instantaneously you will realize that jet engine actually becomes more efficient the more oomph you extract out of it. At that point in time, your diesel engines will not keep up. So if you are basically in Kuwait and these puppies are coming at you, and if they looked at you and they're starting to chase you, yeah, bye bye your diesel. It does not matter. At that point in time, this will like, bro, where are you going, bro? Bro, where? So that's the reason why they are using it. So in this Cessna system, what they wanted is a cheap jet engine, because again, small, cheap, efficient, awesome. But it has to give mileage that is comparable or better than combustion engine, ICE engines that they were using. So small engine, how would they get that extra power? This technology, basically recuperator. So how can they add it? Well, the engine is small and recuperator is being built with newer technology. This system is ancient. The recuperator system is ancient. This has much later current technology, and not to mention, because it's designed to work in the upper atmosphere, the dust contamination is also much lower. And people are working on, be mindful, even though this is a system, it's not airworthy yet. Last time I checked, it's not airworthy yet. And I'm pretty sure there are people working on jumbo jet engines also, but it's always going back to the same thing. Are we adding too much complexity for too little gain? It's generally not a wise thing to do. So people are working on it, and we can expect to see some progress quite soon. Be mindful, ground system we have already sorted. So what we can expect in the future? Well, here's the deal. It's a necessary technology. Now, why this technology became necessary is simple as that. Fuel prices are going up, and consequence of that, energy prices are going up, and it's going up year over year. Meaning, even if like you have 1 or 2 years, it's like, oh, prices have dropped. It's like zoom out a bit. Zoom out. Take price chart, zoom out a bit, and trace over 10 years, 20 years. You'll be like, no, it's constantly going up. So even a little bit of mileage gain that you will basically energy save that you're gonna get from having a system that has a recuperator to like preheat or pre-cool your incoming air for your building, that's a big deal now. We had known about the science long ago, like 50 years ago. We known about the science. We have even built it, but it was like no point in it. It's like the cost of that thing itself was too high. Now the cost of thing is still high, but energy cost is higher. So people are like, hey, how about I invest in this to save? It's like how you buy ink tank printer to save on basically printing cost. So that created a scenario. And HVAC, if you remove industry, right? You take industry, you just yeet it. HVAC is one of the biggest energy consumer. Like surprisingly large amount of energy just goes to keep everything what we call conditioned. Like either warm, so stay warm. If it's basically hot out, stay cool inside. So that takes a lot of energy drain from our grid, and it's everywhere. Be it Pakistan, be it India, be it Nepal. It takes a lot of energy, and even a small gain, like let's say doing that, only improves your energy bills by let's say 5%. That's a lot. Like flat out a lot, especially if a nationwide attempt is done to do that. Like if a nation is like, okay, all corporate building have to have this, overnight your energy consumption will go down. That's how significant this will be. Then we come to the fact micro jet engines are making a quote-unquote comeback. Now, biggest reason why back in the day micro jet engines were not that successful is because they're noisy. Like military actually had a flying jet engine jetpack, but the noise was so high. It's like, dude, do you want like the same issue with Abraham if they did not hit recuperator? Launch a missile just in that general area, it will hit. So same happened with that noise issue. So the idea is that you have a jet engine that is very small. For horsepower that it creates is very small. Like this puppy is 30 kilowatt unit. That's tiny. And that includes the generator. I'm not just showing you just one unit. It's like complete package, quote unquote. That package is designed for EV range extension. And it has like, air compressor and a recuperator and basically jet engine. So it does have the benefit of high RPM. That's why the generator is so small. As in like 100,000 RPM or 130,000 RPM. Super stupid high RPM. Microjet engines generally have that high, super high RPM. Now it does allow to work very efficiently because of recuperator, because of reheating. It can give you low emissions because it's just burning less fuel, which is very awesome. Now be mindful, you may think like, why can't we do the same thing with combustion engine, ICE engines? Problem is that ICE goes boom, and we want that boom to be controlled. You do not want your, like think of this, like what do we have? We have turbochargers. What does it do? It takes exhaust heat, removes its energy, compresses the incoming air. But here's the consequence: compressed air is dense, but it's hot. What do we do after that? We put it through intercooler. We cool that puppy down. Cool, relax. Why? If we send that hot air, there is a very good chance if you open the intake valve, the moment the fuel squirting will begin, boom. You do not want that. It's a boom boom device. It's a very inefficient device. That's why jet engine is so small. Like in the bigger the power scale, the jet engine becomes like, this is my jam. So that's why your recuperator can work on jet engines, not that effectively on basically combustion engines, internal combustion engines. So that's the mobile power plant that companies are developing with lower power efficiency. And recuperator is just a good toolkit. It's not a magic solution. It's not like do this, problem solved. It's more of like, this is one extra tool that you can deploy in order to combat climate change or to save money. Like sell whichever one you want. Like if you are talking to environmentalist, it saves environment. You're talking to corporate, it saves money. So everybody wins. And I like this sort of solutions where it's like everybody wins. So this is a very good toolkit, and this is a small unit that they're working with this sort of heat exchanger. And again, be mindful, our metallurgy has become much more better compared to last 50 years. So we can actually have metals that can withstand exhaust temperature directly. It's like, I got this. And because of the laser welding technology improvement and the fact that now we can 3D print, you can have like very good, like this sort of very amazing infrastructure that allows lot of flow without pressure drop. That was another issue. You choke a jet engine if you put too much strain in front of it. So you always need a flow that is very smooth, very let it go kind of flow. You do not you want the heat to be taken out, but you don't want the pressure to create what we call back pressure. That's bad. So recuperator is a good toolkit, like basic toolkit that is used for air conditioning, high advanced toolkit that is used for jet engines. These are good toolkit that allows us to save a little bit more. Now, if you truly want to save global warming, you have to apply this sort of tools everywhere. Like, this is one tool. I have already covered hundreds of other tools like HVDC, floating wind farm, better solar panels, basically solar panel with thermal energy recovery system, either by hot water or hot air, those sort of systems. So if we deploy these sort of tools, then we can truly take care of global warming. We're not going to solve global warming. It's like, oh, do this. Nah, not happening. But if you deploy hundreds of small tools, hundreds of efficiency improvement tools, over time, it's going to solve itself. It's not going to happen day one, but it can be done. And this sort of tool is really awesome tool because it takes care of both parties. You want to save the planet? Awesome. You want to save basically mileage? Awesome. So this was my presentation on basically energy recovery from Recuperator. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. As always, thanks for watching.